Welcome to lecture 10, CS229. Happy Wednesday. It's really nice outside. I hope you're getting some time outside today. It's like pretty nice. This is like the California you were promised. A little too cold for me, but like I enjoy it. We're going to try copy paste again today. I would like to say that before we started recording, I did show that it actually works. It's just a very disturbing delay. So we'll see how that goes. Today we're going to continue in unsupervised learning. We're going to see the details of the EM algorithm, and then we're going to transition to its non-probabilistic analog, PCA. And PCA is a workhorse algorithm. I use it all the time. One of my graduate students sent me plots for PCA last night about something. And so it is kind of a workhorse canonical algorithm that you should have in your toolkit. Okay. So we'll first discover this EM that discovers our ad hoc algorithm that we did before, this GMM algorithm. We're going to explain how this is a principled element of what we're doing. Then we're going to talk about this classic dimensionality reduction idea PCA, and that's going to be our entire lecture. Okay? All right. So last time, remember, just to motivate you and give you a little bit of time to look at the slide, I'm going to draw some pictures. And this is the picture we drew last time, roughly speaking. We were given a bunch of these photon counts. Remember, this was some plate that we held up. And these were individual photons. These X's are individual photons. And we were trying to figure out what sources they came from. And we don't know the sources. We don't know how many points come from every source. And we don't know the shapes of them, right? Remember we talked about before, we wanted to get these shapes. And the idea that we saw for GMM was we basically had this latent variable, Zi, which was which source it would correspond to. And the difference between what we saw in k-means was that it was a soft assignment. So we would have a point, for example, here. Let's imagine that currently we think there are two sources in our algorithm. This point we may say is 50% in this source and this 50% in this source, whereas this one we're fairly confident that this point belongs to, call this source 2. Okay? And that's what Zij is actually going to be. So that was the clustering strength. But it was a soft clustering, right? So we're going to look at that. And then what we did is after we assigned all of the points and we said, okay, all of these points are probabilistically assigned with their various weights, we then refit the parameters intuitively, the mu j's and the sigmas. So they would fit, for example, both their mean and then some, I'm drawing a bad version of it here, but they would fit some ellipse. Why was it an ellipse? What did the ellipse kind of look like? What does the ellipse represent when I draw it? Exactly. It's a multivariant Gaussian. And so those are its level sets. So those were all the equal probability, equal density things were on an ellipse. And the reason they're ellipse is those are the dimensions, if you like, of the covariance, right? Those are the eigenvectors of the covariance. Okay. All right. Okay. Then we also refit this phi, which we'll get to in a second. This is just a review from last time, which has the proportion, which was the estimated fraction that we had. And we had ad hoc estimates for that last time. If you don't remember them, please don't worry about it. We're going to rederive them now. But this is a way where we could derive them in general. Last time we kind of squinted at it and said, hey, this was where the mean should be. This is where the variance should look like. This is what the fraction is. We just kind of fractional count based on kind of population statistics. Today we're going to derive that, okay? And that derivation is going to be the example for this EM algorithm, which is a very general algorithm, okay? And then as we talked about, it was repetitive. So hopefully this is a review from Monday. This looks exactly like k-means, except for the difference from k-means was, in k-means we had a hard assignment. Here we have a soft assignment. In k-means, if you remember, we picked our new points. They said, hey, these are the points we think are in cluster 1 and cluster 2. We computed the means or their centers. Then we iterated. Here, instead of just picking their centers, which are the mu's, we also pick some statistical parameters, their variances or their covariances, and we fit their proportions. Okay? Otherwise, it's the same. We went from a hard assignment, soft assignment, and probabilistic. Cool? All right. We walked through last time Jensen's inequality, and we're going to use it for concave functions. So I'll only state it for concave functions. That's a terrible line. So this is x, and then we have a function here. Here's 0. We have something, this kind of log x kind of looking function. Here's 1. So it's looks like this. This is log x. Okay? This is log x. Right? And remember the picture here, when we want to look at g of z, so if we take any point g of z, we take two other points, a and b, so this a and this b, and we draw the line between them, which I'm going to highlight here, if I can do it, this green is this green here, okay? That's the line. Lambda is the line between them. And then that is, because it's a concave function, below the line. That is the definition, if you like, of a concave function, that no matter how we draw that chord, it's going to live below the line. We're going to use that estimate quite a bit. And the form that we're going to use that fact in, that we saw looks mysterious because of the notation, is right here. Is that we're going to be able to take the expectation and move it in the right way. And the way to see this again is to think about this lambda, you take A with probability lambda and B with probability 1 minus lambda. This is a simple expectation. Everything on that line is one example of that simple expectation, right? And that's visually saying this. And hopefully this drawing, the reason I hammer on it is, should you ever get confused, hopefully you can remember the log and that it's below. Sound good? All right. Okay, so this is all review from last time. This is kind of where we left off. If any questions bubbled up, please feel free to ask. Otherwise, we're going to keep going through the EM algorithm. Okay, cool. All right, so this was the picture we drew of the EM algorithm. And I want to go through it again because I want to make sure it's fresh in your mind. It's a weird one to look at. So here we had some parameter theta. What are the thetas? Do people remember what the thetas are, what I'm drawing here? What does theta represent? Please. Yeah, please.
It's the vector containing all the parameters for the...
Exactly right. It's the vector containing all the parameters. In general, it will be for kind of whatever we're interested in. Here, it's all the mu's, the sigmas, and the phi in particular. It's all the parameters. Okay, so it's this kind of abstract thing. I'm going to draw it as a one-dimensional curve because it makes my life easier. Okay, not because that's really what's going on. And the curve that we drew last time had this kind of illustrative shape, right? And I picked this illustrative shape for a couple of reasons. One is that it has this nice kind of multiple bumps we talked about last time, that you're going to do kind of a local search inside this. Okay? All right, so this is the way the algorithm actually looks. The way it works is that we start with a guess. Here, theta, I'm going to call it, theta t. And then this point, this is just definitional, is L of theta t. Okay? Because this curve is L of theta. Okay, that's our likelihood function, our loss function. Okay. All right. So what do? We're going to talk about how to construct this object in a second, but I want a picture in your head as we go through it because there's going to be a bunch of math, and then you could get lost in the math. But the picture is what's going to hopefully save you. It's the kind of the intuitive way to understand it. What we're going to do is we're going to create this new function, L of t, where it depends on t. This t and this t are the same. Okay, so it's a different curve that depends on that point. And that L of t is going to be a function of theta as well. Oops. Of theta. Okay. And this is a curve. I've just drawn a piece of it, right? This curve continues. There's no reason it doesn't continue. I'm just lazy when I've drawn it, right? We only care about, this is the region of interest that I'm drawing here, but it's a full curve, right? It's a full curve. Now, what are the properties of this L of t? We'll talk about it in a second, but one property that's true from the picture is that L of theta of t, that is at this point theta t, equals LT theta of t. Okay? So they meet at this point, which I'll refer to as being tight. Okay, that's the name of that property, tight. Okay. The other one is that it lives below L theta. Okay? So this is L of t theta is less than L of theta. Okay? So those are the defining qualities of that curve. What I'm going to do, the other kind of non-definitional but hopeful quantity of that is what? What do we care about LT of theta? Do you remember from last time? What are we going to do with it? Awesome. It's concave. We're going to optimize on it. We're going to try and crawl up this thing and get a new optimal value. Here, it's exactly right. And this will be, say this is the optimal here, which I'm going to call this point theta t plus 1. And then you see what's going on right here. It's the arg max of this. It's the local max. So that's why I only drew this piece, because it's going to go down from there. It's going to have to be some nice concave function. And then we're going to repeat the process. Right? This becomes, oops. We're going to repeat the process, and this is going to be, L theta of t plus 1. Okay? And this is our guess. We've gone from theta t to theta t plus 1. Okay? The E step is given theta t, defining this curve to begin with. That's what we're going to do first. And then the second team is once we've had that curve, we're going to optimize over that surrogate over all the theta t plus 1. Okay? All the theta, and that's going to give us theta t plus 1. Clear enough what the program is? Awesome. All right. Now, intuitively, what's going on is we're taking little convex surrogates, or little concave surrogates, and we're walking our way up to try and get to a maximum. Do we expect that it gets to an absolute maximum? No. This is by my beautiful drawing. It makes it obvious because this G could go spiraling off into infinity. We don't know. Okay? We don't know anything about that. That's a property of L overall. But this, we're going to see, actually does converge. Here's a question.
Why would this insert 30% on that?
Yeah, so let's when we walk through this, see what's going to happen when you do that kind of thing. What this is going to allow us, EM is one algorithm. You could have other algorithms to solve it. That's one answer. Here, what we're doing is we're taking advantage of the fact that it's a latent variable model, and this is allowing us to instantiate it in that way. So there are situations when you could just take a latent variable model and solve that on an algorithm. This is a different algorithm for solving those problems. And in that, you would have to marginalize out over all the z's. So I would try and write down the algorithm that you propose, and then you'll see why this decomposes in there. But for the moment, I think just say, this is a different algorithm.
Isn't it not convex?
Yeah, so this function could be nasty everywhere. But this function will be nice. We're only argmaxing on this local surrogate. So the trade-off is there's a nasty algorithm, potentially that we don't know too much about, but there's a function that is locally going to be nice for us. And so back to the other question, intuitively what we're doing here, if it were, and this is just like what we kind of hope works, is that we have some problem which is nasty, we decompose it in some interesting way, and then it decomposes locally as something that's nice and easier to solve, which is what our LT theta surrogate is going to be. And we're going to do, this is our first example of alternating kind of methods. We solve one thing, gives us a new estimate, we go back and forth, and back and forth. It works. It's like the exact analog of how you would solve k-means for exactly the same reasons, right? Oh, fantastic question. Yeah. But the other function, just like k-means, was, NP hard, if you remember last time, but also was a hard function to solve exactly. So, the underlying function, it's going to be an approximation in the sense that, we hope to get a good solution out of this. We may not have any guarantees. These are phenomenal questions. Others? All right. So now, let's get into doing it. Let's figure out how we construct LT, capital LT. All right. All right, so now what I'm going to do is if I do my job well, there will be a lot of symbols that I can't avoid. But the manipulations will actually strike you as quite simple. Okay? All right. So how do we construct L of t? So what I'm going to do right now is I'm going to examine a single data point. And the reason this is so critical is it lets me drop those scripts everywhere, superscripts. That's really all I'm doing. At the end, we're going to sum over all the data points. This just makes my life easier on this, that I don't have to maintain a bunch of sums. Okay? So I'm looking at one individual data point right now because of the kind of ID assumption. Doing that, I can just scale it by a summation later. All right. So as we've looked at, we want to have this log likelihood that was there before. And our log likelihood function decomposes in this format. So I was asked earlier about, the SGD piece. Well, this sum over Z could be quite nasty if we had to do the, entire decomposition of it. Z could be big. For now, I'm going to imagine it's discrete because it makes my life easier, but it could be a big continuous thing. So this is a way of dealing with these hidden variable models where we don't see Z. Okay, cool. Not to say you can't do something about it, but this is just one way to decompose it. Okay, so back to it. If you look here, what we've done is we're going to do this thing that looks like an insane trick, okay? What we're going to do is we're going to say that for any Q of Z that we pick, okay, non-zero, so it kind of makes sense, okay? And even that you can relax, by the way, even to greater than or equal to 0. This holds. Why does this hold? Well, Q of Z over Q of Z is 1. This looks like a pretty dumb thing to do, to be honest. But we're going to make Q of Z mean something in a second, okay? Intuitively, it's going to be a reweighting, right? If you look at this, you're like, okay, you're going to be up to something with a reweighting. Okay. So the way we're going to pick Q of Z among all of them is we're going to pick Q of Z so that it has these properties. And what does that property remind you of? It's a probability distribution, okay? So Q of Z is going to sum to 1 and be non-negative. This allows us to do something completely notational. Sometimes people argue it's completely notational. We write this expression. What happened here? Nothing. Q of Z, I made a distribution, and I made the expected value, go over Z being distributed as Q of Z, and then I also divided by the Q of Z, which is a scalar. I kind of treated it in two ways. Kind of a weird thing to do, right? But this allows me to think about this as an expectation. And we have tools to deal with expectations. All right. We have exactly one tool to deal with expectations. So this shouldn't come as a surprise. There were not 10 other tools. I guess we have linearity. We could use linearity, which we're going to use a little bit later. We have Jensen. Okay, the last slide. And now what this allows us to do is switch the log. Okay? Now, when we switch this log, this, because it's concave, somehow it's that underestimate property we were just talking about, right? So we have the direction of this. We had the original function, which was this, and we just used Jensen. Okay, so now it has that underestimate kind of quality. And then, well, we stop pretending that it was an expectation. We bring it back out. Okay, now, why did we do this? Well, this is a nice, clever trick to be able to use the mechanism we already had. This isn't like, why it's true. Maybe you think it was why true. There's another proof, but this is a really slick one that just uses Jensen. Okay? That's it. Cool. So now we have this function, which is a natural candidate to be our L of t, and we did it per point. So this piece here holds for any choice of q subject to this. And we select the Q per point. Okay, so if Q had a script on it, I would have to put them everywhere. Xi, Zi, but I would also have Qi. Okay, so every point is going to get to select its own weighting. That's going to be important in what we do next. That's why I highlight it so strongly. Because you don't think it's like one Q that's chosen for all of them. Please.
I have a question. How can we be certain that this function has a different an argmax that corresponds to a different theta than the theta we initially chose, or theta 2 we initially chose?
Great question. So the question you're raising right now, let's get through the algorithm and come back to it. The question you're raising is, why do we know that this is guaranteed to make any progress? And we'll come back to that in a little bit. Why is it that this surrogate that we have here is going to make any progress underneath it? It's clear that it will be no worse. Why is it clear that it will be no worse? Because it's tight, exactly right. We know that it takes at least the value of the L theta at the current point. And so when we do the argmax will be at least that point and potentially higher. So unless it's exactly at the top of this curve, we'll see what happens when it's exactly at the top of this curve, what that means, then we're going to make some progress because the argmax will strictly improve. Wonderful question. Thinking about exactly the right things.
That argmax?
We haven't got, yeah, so it's the argmax from the last slide. Yeah.
Right. So it's monotonically increasing, is that correct?
So yeah, so the theta will be monotonically increasing in the way that we've done here. Exactly right. The L of theta surrogate. Yeah. Cool. That should also tell you something else, that it will eventually, terminate after some point. Yeah.
So could you repeat at a high level why we do this Q of Z trick?
Oh, great. Yeah. So there's two things. So the question is, why do we do this Q of Z trick? So one, the real principal reason is it allows us to use this technology, which is the Jensen piece right here, right? So it allows us to use Jensen's inequality. Q allows us, with this particular selection, says you actually can regard this function as an exponential, as a expectation. And so that gives us a natural surrogate to construct the lower bound. So the reason we picked Q, like it seems very strange to pick it, it's because it allows us to do exactly this step. So it's really an operational reason. Now, if you're asking a deeper question, why these surrogates? This is kind of, if you look at it, you'll see in a second, the way we pick this is kind of just a local surrogate that satisfies exactly that. It's called an evidence-based lower bound. You're going to see when we get through this, that this particular choice has some nice characteristics. In particular, what we were just talking about in tightness, we know how to make it tight. And you'll see that happen in the next couple slides. But so we picked Q so that we could turn into an expectation, so that we could use Jensen. Yeah, go ahead.
Lower bound is what we maximize to get our L.
Exactly right. So this is LT for 1 point, and we'll come back in another slide and actually go and make sure, we have to make sure and verify those two properties, the tightness and this elbow piece. And then we're going to write the sum. I'm just foreshadowing. That will come in like 3-4 slides. You'll see how it's put together. So this is just, right now, LT defined for one thing. We haven't done the argmax yet, but you're thinking about exactly the right ways. How are we going to use it?
And when you say tightness, you mean that it touches once at L of theta, the original one, and is underneath it at all of the other points.
Tightness refers to just the first of those processes, which is this thing here, which they're exactly equal at that one point. And that was what was beautifully pointed out earlier was because of that tightness, when we do the argmax of this is a lower bound because it's on the curve. And so the argmax will give us a better value of the L. That's geometrically what's going on. Awesome questions. You guys got this perfectly. Others? Cool. All right. Okay. So how do we make this thing actually tight? All right. So here is an observation about Jensen's. If we pick P of xz theta over Q of z, this quantity, so that it's a constant with respect to z, it does not change as z changes, then Jensen is an equality. Okay? I'm saying something trivial with a lot of words. Why is that? So if the random variable's distribution no longer depends on z, imagine this happens for a second, then they're tight. Why is that? Well, this thing equals c, right? That's by, I said, if this thing equals c, it equals c. Nothing done here. Log of c equals log of c. The expectation doesn't change that. The expectation of a constant is that constant. Okay? On the other hand, the expectation of this constant, also a constant, is c, and equals log c. So the way we're going to get to tightness here is somehow we have to pick Q of z so that, oops, that was not what I wanted to reveal. No, you saw it. Okay. Anyway, either here or there. Ignore the other slides. Anyway, so how are we going to pick that? So the idea is to pick this so that it doesn't depend on z. And how would you do that? Okay. So I did show you. So the idea here is to pick it as a conditional probability. Okay. So if we pick it in such a way that it removes the information of z, so that Q of z is equal to P of z of x, then that is equal everywhere for all the different choices of z. It is equal to exactly x theta. So we get to pick all those q's. Okay? Now, qz is going to depend on theta and x, but not on z. So we're going to select it for each point xi. Okay? So it's, for all choices of z, we can make this decision. It depends on the xi's that are fed into it. It depends on the thetas that are fed into it. But we can do this, and the end result is, because Jensen was the only thing we used in our argument, sorry to flip back and forth so much, but the only thing we use is this has become equality. And that means it's tight. Okay? All right. So this thing that we've just defined, we now know has this tightness quality, and we've actually shown something else. We've actually shown the full elbow thing, the first two properties. I didn't highlight it, but you caught on to it right away, which is that L theta is less than or equal to this as we sum. Why? Because true term by term. Right? Term by term, we showed every xi is actually less than or equal to for any q that we pick, no matter how we pick the q for this. And for the particular choice of qi above and theta t, we showed this. So it matches the picture that I showed you earlier. Okay, so if you've gotten lost in the symbols are unfortunately heavy. That's just how they are. This is a famous thing, the evidence-based lower bound. It is a concept that people use again and again. As I mentioned to you, one of my graduate students was writing the evidence-based lower bound for their particular latent variable model for a paper that's going to go out next week. If you do diffusion models, you do elbows underneath the covers. They all have them in there. This is a kind of a canonical-based lower bounding technique. Not to say there are not others, not to say there aren't better ones, but this is a canonical one that just uses this information that's in Jensen's and the local concavity. Please.
Do we have something that manage like how wide are these L distributions?
Oh, wonderful question. Yeah, so the question here, all right, okay, oops, I just want to get the conclusion on the slide. So the question is do we have anything? So those L of t's that we thought are actually this elbow function now. It's the sum of these elbows, right? So the question is, do we have anything that manages? What makes a good or a bad L here? And what's going on here, why it's evidence-based, is we're just using the local conditional probabilities for every term. So this is the best we can do by looking term by term and looking at that conditional probability with Q, roughly speaking. That's an informal statement, but hopefully that makes sense. Another way to say it is, no, we don't have any control in this approach of like whether or not L is going to work. That's actually a function of the underlying problem and kind of its shape and curvature. So like, an example of this, why this is similar, is in gradient descent. If you have a really sharp function, maybe it's easier to get to the bottom, or if you have a really wide function, you can get down close to the bottom. Those are properties of the loss function, not properties of the algorithm here, right? Everything kind of was almost deterministic from the time we turned the crank. Yeah. There was randomness. The randomness was in the initial selection that we had. This exactly mirrors k-means, right? So hopefully right now all the pieces click together. You're like, oh, that looks like a lot of unnecessary, needless math. Fine, I admit that. But it's precise, and what it tells you is each one of those blocks fits in exactly the same way. Okay, cool. Please.
I'm trying to understand for any distribution, like can we do this method, like derive the lower bound and like how?
Wonderful question. So you asked, the question was, can we do this for any distribution? So the question, another way to turn that question around is, what assumptions are we making about this distribution? And one which I think, over time, like I think when I was starting out as a, undergrad, grad student, you would see some assumptions and they would feel kind of mild to you, and other assumptions would seem kind of strong. When you see someone write something that says the probability function has the following form, that's usually a fairly strong assumption because it means there's some deep factorization. And we did a deep factorization here. I don't want to scroll all the way back, so I'll just like write it and erase it. We assumed that P broke out in a particular form, right? That it looked like our probability of X was the probability of X of theta, we assumed, had this latent structure that we knew, which was this thing over Z that said XZ of theta. Okay? And we knew what Z was and we had information about it. That's a relatively strong assumption because it rules out lots of models. If you know it's there, like for example, there's some clustering or there's some point sources, then that's a fair assumption, right? There's a Z that has the following shapes. But we have to know a lot of information about Z, right? Here we had to completely characterize it. We had to know kind of roughly, we had to know that it had a number of point sources. We had to know that they had particular shapes. And so that factorization, a lot pulled into it. Now that said, so that's one answer that says, well, this is actually fairly specific in the class, canon of all functions that are out there in the world. In practice, or, kind of in machine learning experience, there are a lot of latent variable models where you decompose in this way and it gives you some amount of information. And so this assumption may seem narrow from my description, but actually there are a ton of models that basically said, no, we're willing to assume this about the underlying substructure, and that allows us to then do much better inference. And so again, it's a modeling choice, like how much you're willing to assume you know about the Z and put in there, then tells you how well your model has fidelity, and then tells you whether or not this method is applicable to it. Yeah, please. Sure.
See, like the features and text and stuff.
Oh, recall what Z is. So Z in this example is going to be, kind of the information that tells you all of the latent or unobserved structure. So the things that you can't directly measure, like in particular, when we run through it, it's going to be like the, strength of the sources of the clusters and all that other kind of good stuff. Like the cluster assignments themselves were Z, right? In our example. So it's just something that's not directly observable to us. No one ever comes at the end and tells us, yep, that's that you got, cluster 5 correct. So Z is the latent structure, the hidden structure from us.
So then how are we able to find Q?
Okay, so the thing that we've shown here, so Z is not like something that is, so Z is hidden from us. That means we can't measure it. But when we're running our procedure, we have a guess for where Z is. In the same way that so you have a hypothesis of where it is. So you say it exists, this soft clustering exists, and then you have an instantiation. And based on that instantiation, we make an estimate. And then we estimate the rest of the parameters, the non-latent, the observed parameters. That's the next state. And then we update and say, oh, how would that have changed our Z? That's the loop that we're going through kind of again and again and again here. The QI of Z is going to be based on the data we have and our current guess of the parameters. That is the parameters we talked about, the sigmas and all the rest of that stuff. What do we think the clustering actually is that we don't observe? And then back and forth. Okay? So like Z here, this probability distribution over Z, think about how we estimated it previously. You had two Gaussians that were sitting there and you had a point. And you said, well, I think given my current guess of where the means and those Gaussians are and their width, I think it's 50% likely or 60% likely it goes to cluster 1 and 40% likely to cluster 2. Now, at this point in the algorithm, I have a handle on Z and I can use it to actually set QZ. So it's unobserved, but it exists during the run of the algorithm. Okay? We make a guess at it. And that hypothesis that there's structure, that's what let us run the whole thing. Awesome questions. Go ahead.
So I was just trying to understand. So, like, if we think it's if we have two clusters, and we're like, oh, this Z is like 50% in this one. Oh, sorry, this point is 50% in this one and 50% in this one. What is Z in that situation?
It's a vector that has two numbers, 0.5 and 0.5.
Okay, it's saying which cluster.
Exactly right. Yeah. Because it's the probability over the clusters. Yeah. Good job. Yeah, thanks. Sorry. Very good. All right. So this is phenomenal. You guys fixed all my bugs on the fly. By the way, as I said, I will try and copy paste later, so you will not be able to fix that. So it'll be unfixable bugs later. Okay? But this is phenomenal. What you have, the E step is we're going to fix exactly those QIs. We're going to do this conditional probability that's going to guess the clustering, which clusters they're in, just like we did in K-means, right? In K-means, we guessed, hey, these guys are in cluster 1, these are in cluster 2. Then we computed the means. Instead of just computing the means, which could have also been written as an argmax, we're going to compute this likelihood argmax, and it's going to be a little bit more sophisticated because our model, instead of just saying whichever one is closer, now has a probabilistic interpretation under the covers. Okay? Why does it terminate? Well, this was exactly the monotonicity discussion. You guys already nailed this, so you're way ahead of me. And the second is it globally optimal? No, because I told you I could draw whatever I wanted over here. It's a local method. Cool? All right, let's see it in action. All right. So, let me see. I want to do this. All right. Please.
Actually, think about the same about how wide are these curves.
Sure.
Because this local, it just means like it's not global. It doesn't mean like it will go like whether this one will go as long as there's a slope. This could jump over local minimum because this.
It's certainly we haven't shown anything here that would suggest like it's certainly possible. So one thing you mentioned there to draw back in your picture, there's nothing I've told you that ruled out that, for example, there's a little bump that goes down here that it managed to go over. It's possible. Yeah, that it jumped, and so then the L2 got something that jumped out of that neighborhood. So there's nothing that says anything that looks like that. And actually, that's not true for gradient descent either, right? Gradient descent has a step size, and it will jump as well. And so, yeah, these algorithms do have that property. You're exactly right. All right, so here are the two steps. We're going to go through them in a second. All right? So we're going to look at this EM for the mixture of Gaussians that we had there. These are the two steps that we had previously. And for each data point and each source that we have, remember we know the number of sources, we're going to try and find a soft assignment to PZ equals J. And we went through this actually before, so happy to go through it again. But the way we did it, if you remember, was we decomposed with Bayes' rule. That was the basic idea, right? And so once we had this, we had a probability distribution here that we wanted, and we had this conditional probability. Okay, all right. The more interesting, so here we had all of these, these different distributions that we had underneath the covers, and we would score how likely they were into each cluster. This was we had two bumps. We looked at the bumps, we looked at how likely they were, and then we were able to actually do the assignment. Okay? All right. So that was just Bayes' rule. Okay? Now, right, let me just draw the picture here because I think the picture will be more clear of an explanation for that than anything else. Okay, so how do we do it? Oops. All right. All right. So now, I give you these 2 points. Let's run through the choices that we have. And it's here. And this is my point. Now, this is my xi. This is mu1, this is mu2, and then there's, they have their sigmas. I'm not going to draw. Okay, So we did this in detail previously, but I want to make sure intuitively it's clear that you can derive this. So we want to compute this probability of zi given the point that we've observed. So we observe the point, we have the mu i's, we have the mu 2's. How likely do you think this point is? What do you have to compute it? Exactly right. You have the entire probability density that you can use to compute exactly this thing from the model that you have underlying it. You have all the theta i's that gives you a likelihood for being in this and being in this. Now, intuitively, just if all two are equal, you would probably assign this point more likely to cluster 1, right? So maybe you say this is 60-40. Where do those numbers come from? It's a ratio of the likelihoods. Right? That's what you're going to use to compute it. It's Bayes' rule. That's exactly what Bayes' rule does. We did this on the board last time, but I just want to remind you. And then the question is, here, if you knew that this mu2 had 1,000 times more points than mu1, you would expect that your likelihood that this actually belonged to that cluster, because it's 1,000 times more likely, would go up by some amount. And that amount is exactly the Bayes' rule decomposition that we got last time, where we looked across each of them and then we summed, right? So we computed the probability that it was according to cluster 1, cluster 2, and we normalized. Ask me a question if that's not clear, and I'll write out the entire math. We can go back and do it. But we did that last time. Good enough? Right? It was just the comparison between the two, right? So basically you computed, z, oops. I don't know what that did. Awesome. Want that off the screen. All right. So you'd compute zi equals 1, let's say, given all the rest. And how you would do it is you would compute then p, I'm going to just do it for this simple one here. We would compute and normalize by p of z1 given 1, blah, 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 plus p z2, z1 given, or zi, sorry, zi equals 2, okay? Blah, blah, blah. We would just look at the normalized ratio of these, and this is what Bayes' rule told us to do last time. There's nothing mysterious here. It's just comparing those densities that we had. This may be disturbing to some of you because these are densities that I'm comparing, but that's okay. Okay? Those numbers are meaningful. Okay? If that bothers you, I would say go back, check it out. By your faces, maybe some of you are bothered. You could also ask me questions and I'll tell you more about it. Okay? Does this make sense? This is how I assign the value. How do I compute this thing? Anyone? How do I compute the probability that's in one of the clusters? Exactly right. I just take that p of z that we have with all the x, 1 over square root of 2 pi, blah, 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 covariance, monohobeless distance, all that junk that I'm trying to avoid desperately writing on the thing. But if you make me, I'll do it. Okay? And that gives me a number. That's this number. Then I do the same thing for z2. Now I have those numbers and I just compare them. And that's the distribution. If I had 5 of these sources, I would get 5 numbers from the 5 different clusters, and I would go back and do it. Please.
You mentioned that, we knew we had like 1,000 points in blue or whatever.
Yeah, awesome.
Where are we assuming getting this?
Right. So here, when we did this decomposition, there are 2 factors that go into the probability distribution. One is the normal distribution that comes under here, and then is we multiply it by how likely it is. So for example, in the case where pz of 1 equals blah, 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 and all the rest, its probability would have baked into it when we did the decomposition, right? So the source, the mu I and the sigma are kind of independent of the phi 1, which was the term that said how many are in this particular thing, and we would multiply against it. And so then this term would become like multiplied by 1,000, right? And so we would have those two would go back and forth. It would enter linearly in the way that happened. And that was exactly what Bayes' rule told us last time. Sound good? Yeah, I think the notation makes this obscure. I think if you just write out what I would suggest to do is just write out what the numbers are and actually try and like plug it in, like code up some Python that does it once. Then it locks in your brain. These are all just vectors that have horrible notation. Okay? You just add them up and do them and like life is good. And it makes a lot more sense that way. Okay? Maybe not the best advice for a teacher to give you, but whatever. Yeah, just do it and it'll be good. All right? Anyway, any case, let's get back to it. Okay. Let's go to the second step. Okay, so what we got out of the first step, just so we're clear, is we estimated all those QIs, right, for each one of them. And hopefully this answers the questions that came before. Hey, now we have an actual guess for every Z of how likely each individual point is. We never observed that, But we now know, for any point xi, we have a probability distribution that we've constructed, which is our guess, our soft assignment. Just like in k-means when we guessed, sometimes we were wrong, sometimes we were right. We're wrong and right here too, right? It's going to converge over time. This isn't a statement about the world. It's a statement about the algorithm's current belief. Good enough? Awesome. All right. So now we're given all these clusters, and we're going to estimate everything here. The phi, the mu's, the sigmas, everything. I'm sorry that the sigmas change, but conventionally they do, and I can't do much about it. Okay? All right, so here the dimension greater than 1, i.e. d equals greater than 1, so mu j is going to live in rd, and sigma j is going to live in rd by d. If d is equal to 1, we confusingly write this as the lowercase sigma, but I'm going to write in the uppercase sigma because it's going to make the math a little bit more transparent what goes on and eliminate a stumbling block, I hope, when you get there. Remember, these covariance matrices are positive semi-definite, and they are symmetric. Okay? Cool. All right, so let's do the M step. It boils down to computing a bunch of derivatives. Okay? All right. It's not super pleasant, I'm not going to lie to you. This section is not fun for either of us, but if we go through it, we'll understand it and we'll all be happy. Maybe. I don't know if your happiness is deeply tied to understanding this. Okay. Sure.
What about this process motivated the need to construct and optimize a surrogate function as opposed to what we've been doing before with gradients?
Awesome, yeah. So this is a great question. So this has come up. So if we, for example, so there's two ways to understand it. One is, here we have extra structure about the function. We know that there exists these huge set of hidden variables that we're going to optimize. And so we have to come up with an assignment for them in some way. So, if you go and try and write down gradient descent for this, and you have this big probability distribution, you'd have this gigantic marginalization where you'd have to do something about the z's internally. This is not to say you couldn't do something about the z's, but this is one way of handling the fact that we know the probability distribution factors in this way that you kind of hypothesize doing it. It's the same way you could say, like, why can't I just run gradient descent to solve the least squares cost for k-means? I guess in essence you kind of could, but by hypothesizing these kind of where you switch and score, that gives you this extra little bit of structure. Yeah, you've got it perfectly, I think. Yeah. Cool. Awesome. Other questions? Fantastic. Okay. Okay, so it's all computing derivatives. Recall, we just computed this stuff. This is just a definition. Xi, once I give you the cluster, this is just a fancy way to say it has that nice Gaussian shape on it. And this is the weight, the strength. This is how often we see each one of the clusters. Okay, so this is just reminding you of the model. Nothing's happened. Now, in a previous lecture, I wrote this out. Hopefully you remember this monstrosity. What is this? Yeah, it's the multivariate Gaussian distribution in all of its beautiful glory. So I try to hide this from you as long as possible, but here it rears its head. And why it rears its head is you have to compute some stuff. So we're going to compute some derivatives on this. And I'm going to do a little bit of sleight of hand to try and make it a little bit more cooking show-like so that you do it, but hopefully this makes sense. All right, so how are we going to do this? So to compute the value of that argmax, we have a good tool in our tool set, which is we are going to compute gradients, and we're going to look for critical points. That is, for example, for one of the parameters we want to estimate, mu j, the means, right, which are there, we are going to compute a derivative here. Now, from the last lecture, what I did was the cooking show version. I was like, oh, mu is probably like I weighted some stuff, and then I weighted some other stuff, and I got this expression. We will get the same expression. It will just be more painful. Okay? But the good thing about suffering on this thing is that you will then be able to suffer in many other instances to compute this when it's not so obvious. And you'll be able to check your work. Okay? But we're not going to do anything complicated. You're going to have to compute derivatives of mu. Okay? It's, again, not the most pleasant thing, and we do have software that does this for you, so, it's of questionable utility. I don't know. I don't know why me do. I'm like having a real-time debate of like why it's valuable for me to do this with you, but I think it's to like vamp so you can ask me questions. Okay? So that's my rationalization for doing this. Okay. So we're going to compute the derivative. We put the log in, we cross this guy out. This one has no mu j to speak of, right? So we knocked that one out. We're computing a mu j vector. And then I've pulled out all the weights and all the rest. Maybe this should have been divided. Maybe that's this is this wj. Good. Okay. All right. Life is mostly good. That should have been crossed out, but it doesn't matter. Okay. Now we have this character here. and we're going to compute mu j. Now, you've seen that character 3-4 times in this course already. So hopefully this is familiar when I do the next two steps, which is I'm going to take a derivative. I'm going to get that this character, this covariance matrix is there. Why is the covariance matrix sub j? What does that mean? It's the covariance for the jth center, right? So remember we had j sources. It's the jth one. I get all these weights. What is the weight telling me here? It's telling you how likely you are to be in that cluster, right? We took the z's, we did that. All right, cool. So that follows through. We get the sigma j. I pull out sigma j here. I want it to be equal to what? What do I probably want to set this thing equal to? 0. Perfect. And then boom, why am I able to take why does sigma j not appear in this expression at the end? What was I doing here to here? Please. Multiply both sides by sigma j, and because, I can do it on the left, but because it's full rank, it means this term must be 0. Okay? If this were rank deficient, there could be non-zero elements here. So I've concluded that this thing has to identically be 0, which gets me back. Everybody more or less happy with that? Ask me to slow down if not. You've seen this derivation. You saw it in GDA. You saw it probably in least squares in some way. The variant that came in is we added in these weights, and the weights were tracked everywhere. This gives us exactly the thing that we intuitively reasoned about earlier. Cool. So far, so good? All right. Okay, I want to highlight one other one for you. So the rest of this goes exactly as you would expect. I'm not going to compute the rest of the derivatives, I hope. Just checking my notes, make sure that's not a lie. So I'm not going to compute the rest of the derivatives. You can do all of them. Let me pull out one thing that seems to get you. If you took like calculus in high school and you forgot about calculus stuff, all the rest is, by show of hands, who remembers Lagrange multipliers? Oh, awesome. Then you don't need to do any of this crap. All right, cool. All right, so Lagrange multipliers, you multiply by lambda. I can derive this for you, approve it if you want. It's not a big deal, but you have to do it when you're dealing with constraints, and the phi's are constrained. If you drop that, you'll get weird answers. Okay, you can see exactly how they'll be weird, but you would have an extra degree of freedom if you didn't put in the Lagrange multiplier. Okay, and the TAs have notes. I also have like a proof of this, which I think no one cares about, but I'm happy to show you. Okay, but remember this one, since you all raised your hands. Just remember that you have to do this when you have constrained variables. Okay. Cool. All right, so the message is EM recovered our ad hoc algorithm. It was still the same gradients and set things to 0 and all the rest. You guys got the great overarching picture, right? The great overarching picture is big L thetas in the background. We construct these LTs. We did it in such a weird way that we could use Jensen so we could pass from the original function to this lower bound. We knew exactly when it was tight, which is how we picked these QZs that were exactly the conditional probabilities. That was another way of saying that those were our best guess of clusters given all the information we had. So there's a sense in which like you're just using Bayes' rule and you're like, oh, that's simple, but that's also reassuring, right? You're not doing something kind of outside the bounds. You're just saying, given my current guess of parameters, this is my best guess of the clustering. And then I go back and forth. It's just formalizing exactly what you saw in k-means, exactly what you saw in other places. Okay? Cool. Awesome. Time to move to our last topic. Principal components. All right, as I mentioned, PCA is a workhorse. It's often misapplied, but that's only because it's applied so often. People use this everywhere. It's a very good dimensionality reduction technique. Sometimes you can use it to visualize your data. Sometimes people use it for featurization. It has all kinds of uses that people have tried for it. I'm going to try and motivate the components for it right now. I found it to be something that I use quite frequently, candidly. Like I just run PCA, and you can compute it much cheaper than you realize, even on big data sets. So it's like, even on large data sets, you can compute a PCA, a small, what's called a thin PCA, reasonably efficiently. All right. So here's the data that we have. So we're given cars, and we're given pairs of these cars, okay? And so the idea here is we have, not a very good axis. This is going to be city miles per gallon. Highway. I have to say, I really like ICE cars. So if you're an EV person, I don't mean to offend you, I guess, but I like the way an engine sounds. Anyway, neither here nor there. Just a small fact. All right, back to this. Okay, so down here are what kind of cars? What kind of cars have terrible highway miles per gallon? This is a general fact about the world. It's not a machine learning fact. These are SUVs, trucks, things like that, right? Good enough. All right. Then you have a bunch of economy cars there and here. You have these hybrids over here, which have, great miles per gallon, okay? Now, a couple of these things, because they're city versus highway, some have pretty good highway miles per gallon, but not great city miles per gallon, right? So as I said, these characters, I don't know, these are hybrids maybe. This doesn't really matter. I don't know why I insist on telling you these stories, but, that's a terrible color. These are SUVs, okay? All right, we're very happy with ourselves. All right, so now the question we're after is, give me the principal component. That's the way we're going to phrase it. Here, by the way, this is one of those annoying terms. If you hang out with machine learning people too much, they'll say things like the ideas are orthogonal all the time. It's very irritating, but they'll say that. They'll also talk about the principal component of how we're selling something, okay? They mean this, okay? But they don't usually use it correctly, so it doesn't really matter. Okay, now intuitively, we kind of want to find out this direction, right? That looks like the kind of direction that's there. So how do we pick that direction or vector? And that's what we're going to get at. We want to know the direction of kind of maximal things. On this data set, it hopefully is pretty easy to see. There's some cars that are better at, burning gas efficiently and some that are poor at doing it, okay? We want to pull that axis out. Okay. So what we're going to do is we're going to center the data. That's the terminology. And this is what centering means. We're going to take this data back and we're going to move it to the origin. And the reason is that we're going to think about PCA as going to look for the directions of maximal variance. And so this is basically making sure that our data intuitively has zero mean. Okay? This is operationally why we're doing it, is to make the math work, but we'll see. All right, so we take all of them, we add them up, and I think the mean is somewhere around here. So let's see if I can draw that thing here. So we're going to draw these axes. Oops. Well, whatever. Things happen. It was fun while it lasted. All right. So here is our new mean. We just shifted everything, okay? I don't have a great animation, but you should just picture it shifting all back to zero via this transformation. Okay, so this is now mu. I took the original data and I subtracted it off, and that's what I did. Sound good? Right? Now, the problem will be, as we'll see, if we don't capture, this is just some generated data, if we don't center, then we're going to get these kind of weird variations that they're going to point towards the mean of the cluster instead of the components of variation. So if you look here, this character varies along this axis, right? But because it's way far away, you just compute the wrong vectors, okay? So this is just to say, if you don't center, it will go wrong. So we assume that the data are centered, and that's going to be important in all of our analysis as we think through it, that the data are mean zero. So often people will run what look like a PCA computation, forget to center their data, and they'll have a problem. Okay, cool. All right. So here's how it's going to be. Here's our drawing from before. What we're going to try and do is we're going to try and find two unit vectors, U1 and U2. They're going to be unit vectors, and U is going to be intuitively the first principal component. I will make this precise, but it's going to try and capture the maximum amount of variation in the data set, okay? And then mu2 is going to capture the second amount of variation in the data set, mu3, and so on. Intuitively, these are going to look like eigenvalues of a particular matrix. In fact, we'll show that in a second. That's basically what they're capturing of the underlying PSD matrix, okay? All right? Now recall when we do our analysis and derive this, that any point can be written in an orthogonal basis in those coordinates, right? So if I have U1 and U2 that are indeed those orthogonal unit vectors, so it's an orthonormal basis, I can write alpha 1 and alpha 2 to exactly recover X. Now, when we're in high dimensions, we can write a huge string of them, one per dimension. We're often going to chop them off and take the top three. And we're going to have to pick which of those components we want. Okay. So the question we have now are, how do we find those directions? I'll tell you about some caveats about how to use this, and then we'll talk about reducing dimensions, like 1,000 down to 10 kind of thing. All right. Now, one other bit of pre-processing is this kind of rescaling behavior that we have. And I'll kind of illustrate it here because I want to give you caveats that are useful to you when you use this. So the other pre-processing we will typically do is we will rescale the data. So if we have x1 to xn that are in RD, we first center the data. So we remove the mean. And then 2, we then rescale the data so that if we had things like feet per gallon or miles per gallon, we actually do it. Now, the way we do that is we compute the variance per component and we scale them by the variance. So they all have about the same scale on them. If you had feet versus miles, right, you would unfortunately think that miles was a huge component of variation, right? Or feet was a huge component of variation because there's so many feet, right? It's pushed out in a huge number. And so you would get that incorrectly. So you normalize so they're all about the same distance for the coordinates that you're given. Please.
Sorry, just a couple of slides back. Can you explain what you mean by so U2 is the second, roughly the difference?
Oh, U2. Yeah, so U2 is going to be the second component of variation. So here, what it's going to be is it's going to, in the example, so that was a statement about the example. Let me go back to it so I can highlight it. Did I not draw it here? All right, so here, this component of variation, it's going to be roughly the difference between how good you are on the highway and how good you are on the road. It's just saying that that's the difference. Like yours, and this is an intuitive statement to say intuitively the way you should think about principal components is, you know, in this data set, it's kind of it's the how good are you in miles per gallon, and then how do you vary among something else in that other direction? Maybe that. Okay, this is more of a story than it is a formal statement. Yeah, wonderful question. Awesome. Shall we? All right. Okay, so the first thing we need to do is, how do you find a point closest to the line? All right. All right, so let's draw this. So we have a line, and we have a point. Okay? Now, intuitively, should be at a right angle. We'll prove that in a second. Okay? But how? All right. Now, how am I thinking about this line? I'm going to write this whole thing out by hand, and then it'll be easier to do. So the formula for the line is, it's the set of t, u1, such that t is an element of R. Okay? That's what it means to be the line in direction u1, right? I just take all the t's that are possible, and I just multiply them by. Okay, so far so good. All right, so now let's figure out exactly how this works. So the first thing to remember about this component is I can rewrite this term here as x squared plus alpha square u1 minus 2 times alpha u1 x. Okay? Please. Oh, yes. Good catch. Perfect. Thank you. The norm is squared. Okay, now, in my head, that doesn't matter too much because it's 1. But yeah, awesome. u1 is 1, but you're exactly right. That was a mistake syntactically to be 1. So that one goes away. When I'm minimizing this character, right, what is my trick? Oh yeah, this is the inner product. Sorry, we don't use annotation. Yeah, sorry. U1 transpose X. Cool. Okay. So when we differentiate this character, what happens? Well, what we're minimizing over is alpha. So what do we get when all is said and done? Well, I have it on the next slide. So is it clear enough what we're doing? We look across all the points here on this line. We try and pick one that is the smallest distance away. We've written the form of this. We've just transputted the form here. And now we're going to try and solve for alpha, which is going to be taking a derivative, because this is a nice convex function in alpha. All right?
I beg your pardon. Alpha being the point on the line to U1 that is orthogonal to the projection of some given point onto it.
Alpha is the scalar. It's the index. It's the t in my last notation. So here's the picture another way. So what we had is remember we had TU1 where was the entire line. T is an element of R. And then here, alpha U1 is some particular point on there. So alpha would be, we're ranging over alpha as ranging over this line. Yeah, some scalar.
Why is this more efficient than just computing the orthogonal projection of each of these points on the line?
Great question. So first what we're going to do is right now what we're deriving is just the nature of how to do the closest point to the line. What you will see in a second is this guy is the orthogonal projector. Okay, so it's like just going to fall out from our analysis that this one is the piece that we're after. Yeah, it's the same. Yeah, awesome, cool. So when we did this, when we computed this derivative and set the derivative equal to 0 and use u squared equals 1, we got this expression, right? So this is 1. We got 2 alpha. We got minus 2 u2, set it equal to 0, boom, we get that. Clear enough? Ask a question if not. Just computing that piece. And then as was pointed out, which is great, is suppose we have mu1, uk, element of RD, we have to use this fact that they are orthogonal here. How does that help us? Well, the closest point to the subspace, so now in a higher dimension, say you have instead of a line, you have a plane, or you have a hyperplane, or something like that. You want to compute the closest point. Then you use exactly the same decomposition, and boom, you get exactly these minimizers. But for this decomposition to work, you have to use that they're orthogonal. So hopefully this is a review. If not, please ask a question. You have a question? Oh, don't worry about that. All right. Sounds good. Okay? So this is exactly as was pointed out, which is wonderful. This is the process of projecting onto the set of vectors spanned by mu u1 to uk. Sorry if I keep saying mu on accident. Just wired into my brain right now. I mean u in this section. There's not yet a mu. Okay? And it will always be 0 in this section. Good enough? Cool. Now, the other bit of terminology is this is called the residual. This is the distance to the line or the plane. The residual squared. Okay? So let me show you a picture. Here's data points. Here's a line through them. Here's some residuals. Okay? So maximizing the projected variance equals minimizing the perpendicular residuals. Those two things are actually the same. We were maximizing how much we explained it away, right? We could also minimize, we could either minimize the residual or we could maximize the explained variance. Okay? Let me be more concrete. So we can maximize the projected subspace of the data. In this case, we sweep over every u, we look over all of the data, we dot it into xi squared, and we try and maximize that quantity. This says, as I sweep u through it, I try and find the direction that hits as many of the xi's as possible, okay, in my data. And that's why if like some of the xi's had really big scalar values, they would contribute quite a bit to this. Like that feet example where all of a sudden they're all multiplied by, approximately 5,000. That would make them skew a lot in that direction. Okay? That's why we have to compensate earlier by normalization. This term also looks a heck of a lot like a covariance matrix. And we'll build that up in a second. Okay? You can also minimize the residual. So let's look at some linear algebra to solve this character in general. Clear enough? All right. Now, by show of hands, who remembers eigenvalue decompositions? Which matrices have them? All matrices? No matrices? What? Symmetric. Yeah. If someone asks you, there are notions of eigenvalues for non-symmetric matrices, you should run from them. They're weird. Anyway. For our point of view, everything's symmetric, so it doesn't matter. Okay? So A is a symmetric and square matrix. Then there exists these two characters who have the following properties. Okay? U lambda U transpose equals A. So decomposition. These characters are orthonormal, that is, they equal I, and they're unit normalized. And lambda is a diagonal. Those lambdas, the lambda i's, little lambda i's that are on the diagonal are the eigenvalues. And by convention, we order them in this way. Okay? So like you'll typically sort them, principal eigenvalue down to the rest. Okay? If you recall, every eigenvalue is associated with an eigenvector, okay? That eigenvector is the ui, is the eigenvector associated with lambda I. And this is just showing you that if you multiply a times ui, so you have a times ui, this character is going to be exactly ei, which is the standard basis, times lambda, which is then going to give you a lambda I, because that's the only term that survived. Boom, boom, boom. All done. And then you get back lambda of ui. So it just says a times ui equals lambda of ui. This is the traditional, the eigenvalue equation. Okay? The pencil equation. All right. So again, evoking pictures you've seen earlier in this course, phenomenal plot-lib pictures. If you have all the eigenvalues 1, you get something that kind of looks unit circle-like, the stretch. Okay? This is the level sets of the linear function. And or you get these nice ellipses if you make them tilted in some way. Okay? Please.
Two questions. One, are we doing a z-scoring for each one of the values? And two, what do we do with missing data?
Yeah, wonderful question. So the question is, are we going to do a z-scoring here? You don't need to. It's a nice pre-processing technique. Here we're doing just what we're doing to make everything go through are basically 2 pieces, which is we're sliding back to the origin so that we actually don't have that problem where there's something off in this direction. We just get the direction to the body rather than the component of variation. Think about this as, as I said, it's the variation distance. So that is quite important. The second one that I highlighted is if you have different scales, you typically will normalize them by taking the empirically variance in that direction and scaling them so that 1 unit of variance in one direction means the same as another unit of variance in the other direction, roughly speaking. This is important in data and comes up quite a bit. It's actually technically not necessary. Neither of them are necessary. If you're asking, are there other pre-processing techniques that you could use to indeed get better or more confident answers from them? Absolutely. But these are the basics that you need that people seem to run into most of the time. And what was your second question? Sorry if I didn't answer. Oh, missing data. Yeah, this doesn't do anything about missing data. If you have a data imputation problem, typically what people will do is estimate some data and then go back and compute it. That's one way to do with it. More egregiously, people will drop that data on the floor and then go on. But missing data is in general a hard problem, which, unfortunately we don't talk too much about in this course, but is an important real life problem. But this data we imagine is complete. Yeah.
You mentioned that the bigger the residual, the less the variance. That feels kind of opposite. Usually, is it?
Oh no. So if you have a large residual, you have a large variance.
And why is minimizing the residual the same as maximizing the variance?
Maximizing the amount that was explained. So remember when we did the maximization, maybe I said something that was confusing. So I want to make sure this is clear. When we go back to this min versus max. When we went to this one, what we were maximizing is the explanation of this. How much did you actually take as it was going, which in some ways is one piece, versus minimizing the residual, right, on top of both of them. And so this was we were maximizing the amount of data that's in the projected subspace in the first piece. Yeah. If I said something less cautious than that, then please let me know. Okay, so let's go to eigenvalue compositions. So remember, we can take a vector x and we can decompose it in this nice, beautiful way, which is a wonderful thing, by the way. It happens in linear space. Doesn't happen in a lot of spaces, but it's nice that it happens in the ones we care about. And as before, we can compute this x transpose x, right? This is what we want to do. So how are we going to do it? So we write x in this form. We multiply by a scalar. So because it's now in this nice basis form, it's in a scalar. The scalar changes the weight. We get back the x that's there. And boom, when we do the dot product of x into this, because x can be decomposed, we get this nice form. We get lambda j times the alpha j squares. Okay? So just to make sure it's clear, all I've done here is I've taken x, I've plugged it in 2 spots. I use the fact that when I multiply u in either direction times the u, I get out this nice equality to get the EIs and the EJs. I use the EJ times as a diagonal matrix is lambda j, and indeed I get out this nice beautiful form here, okay? Which has many fewer free parameters than my original A's and all the rest, right? Just very few parameters in general. Okay, cool. All right. So why did I tell you all that? So now we can write maximizing this function as a scalar over this. And this is a much potentially easier expression because it's now maximizing over all the alpha that are unit norm over this square term. Okay? Please.
Sorry,
Yeah.
I'm just confused while we're doing all this. Like, if we have data, we have coherence matrix, we can just find like diagonalizing
So that's basically what this is doing. So what's going on right now is we're showing how when we actually get the desiderata that we had, which was to maximize the subspace or to minimize the residual, which we'll show later, those things boil down to basically this eigenvalue decomposition, and we're making sure that that process is really clear. There's practical things that you have to do normalization, but what's popping out right here is now we reduce this to something that is this XTX, this maximum over all the explained variance, is actually just something in terms of the eigenvalues. So now we have a quantity in terms of the eigenvalues, so we can understand exactly what's going to happen, where the principal component is going to be in this case, and then by proxy in many other cases.
So we're proving that actually is the best.
We're proving that your intuition about we should do a decomposition on the eigenvalue of the covariance matrix is actually kind of what PCA is doing. Those are the principal components of variation, and they are the eigenvectors of the underlying matrix after you do this transformation. Yeah, that's the content. You got it right. Perfect. Awesome. So which X attains the maximum here? Someone tell me? In this language. So among all these alphas, which one do I pick over here to maximize this quantity? Lambda 1 to lambda 2 are decreasing in decreasing order. You put all the mass on 1, right? You pick an eigenvalue. Now, what if lambda 1 equals lambda 2? So the first one was, take U1, it works. What happens if lambda 1 equals lambda 2? Well, that answer still works, but so do many others. In the first case, if they were strictly separated, if lambda 1 is 1 and lambda 2 is 0.5, then if you don't put all your mass on U1, you lose. You don't actually solve the max. If lambda 1 and lambda 2 equal each other, then picking any vector in that subspace, any combination of U1 and U2 is also a maximizer, correct? Because they both have the same lambda 1 and lambda 2, so I can move around all over the place. Why is that weird for PCA? If I want the principal component of variation, and lambda 1 and lambda 2 are equal to each other, there isn't a single direction. There's an entire subspace. And worse, what happens on my data is, if lambda 1 and lambda 2 are close together, I can get a potential instability. Is it clear why? Because as they get together, I'm maximizing, I'm getting something where the separation between those eigenvalues is implicitly what I'm looking at in my data. If the third eigenvalue is much larger than the fourth eigenvalue, then it's possible that's a good separation. I can reliably identify the top three. But if they're close together, the top three eigenvalues are all close together, the coordinates that I get back don't make sense. Does that make sense? I will have mass, for example, on the first three coordinates, U1, U2, U3, conceptually. They're not the basis coordinates, but in the U coordinates. And then the rest may be 0, that I can say. But their actual values, if I were to feed them into your machine learning algorithm, and you had some linear classifier, there's no reason run after run they would get the same information. So if you had a weight on one feature versus another feature, you would have a problem. Does that make sense? Okay. All right. Okay, so this slide basically shows, as we go through maximizing this original quantity that we cared about, those were just facts about eigenvalues, that we can expand this character. And this thing here, after pushing all the values, is the covariance data because we subtracted off the mean. So back when we talked about it as motivating all these bad things would happen, if we want to interpret this matrix as a covariance matrix, we have to subtract off the mean, because otherwise these guys need to be x minus mu, right? There is a mu, hence, it reared its head. It's 0 because we whitened by it. Does that make sense? So we are estimating the covariance when we do the PCA. That's all that's happening. And the first eigenvalue of the data covariance matrix is the principal component. Right? Now, I hope by giving you kind of this detour through what the underlying math is, you can see some of the ways that it goes wrong now. It goes wrong if you don't whiten it. Potentially, you won't get a principal component. It goes wrong if the scales are different in some way. And if your underlying data doesn't have an eigenvalue spectrum that is separated, you're kind of toast. Okay? All right. So again, this is the way people use it. And so this is one of the things, as you mentioned, people will often do this dimensionality reduction. It really only makes sense if you have all of those vectors to be distinct and separated. Otherwise, when you run it again and again, you're just picking potentially something in the subspace. And that can be quite problematic on your data. Like you send out your data, you do PCA on it, you learn some model, you come in with new data, you do PCA, you get, because of the fact that they're not separated, you get different answers, different coordinates. Your machine learning model may not work on top of that if you use it. So using it for dimensionality reduction, I'm not a super fan of. Okay, you have to be careful about that if you do it. Okay? Multiple dimensions I won't go through. It's the same argument with matrices instead of vectors. And one thing that I did want to say, which usually comes up, is you can actually measure these sums. How can you measure this sum? If I told you to compute this sum of a matrix, and I give you the matrix, it's some wild, nasty matrix, how could you compute this character efficiently? Anyone remember? The trace. I just sum the diagonal elements. So this one I can compute quite a bit. And this I can also estimate once I have the directions that I've actually computed. So in particular, I can compute this without having to compute all n squared things. If my k that I pick is like 3, I can look and find those 3 directions. I can compute their eigenvalues, right? Because I now have their orthogonalization. I multiply them by the matrix. They will be of the form lambda times ui. So I can get all those values. So I can get lambda 1, lambda 2. And this I can compute by the trace. Please.
I'm just trying to understand, why do we want to reduce dimensions again? Like, why do we not just want to keep like all these data?
Oh, great question. So part of what goes on when you have high dimensions is if you have many high dimensions that are, so there's a couple of situations where you want to do dimensionality reduction. One, as we talked about, is you're analyzing your data and you just have a sea of numbers about various things that look the same. The high, city versus highway miles per gallon was an example of like, I'm not sure I really care about that. I just want a car that gives me, good miles per gallon or something. Then that's a data reduction thing where you want to take many variables. And that was a simple example, but in general, you may say, look, underneath my data, there are really only 3 things I care about, 3 directions or 3 kind of pseudo features that explain almost all of my data. If that's the case, then your data, instead of living in a wild n-dimensional space or d-dimensional space that's there, right? It has all these zeta vectors. It actually only lives in this subspace. Then you can make stronger inferences about it. And so when we do dimensionality reduction, there's a lot of both theory and practice that says when your data lives in this huge high dimensional space, but actually has a smaller subspace on it, finding that smaller subspace allows you to exploit it. We've used this is kind of the capstone to a bunch of stuff that we've done over the last week or two, where we've said there exists some structure. And what I was trying to point out here is, here we're making kind of, although everyone uses PCA, it's really making an assumption that the subspaces are well separated in your covariance. That is mathematically what it's doing. So that may not seem particularly strange to you, like, oh, I just compute the variance and throw stuff away, but that's when it makes sense. In contrast, the stuff we were doing with EM was, oh, we assume that there's some latent structure that's there. These sources, they have the shape of Gaussians and we don't know the exact parameters, but they're still assumptions. So those assumptions are the quite important thing to me. But why we reduce dimensionality is because we think that that makes things more predictable. And so a lot of classical machine learning is about doing, from the wild sea of measurements, finding the most important.
Like a real scenario, you just have so many types of features usually that you want just do much more like that.
Yeah, exactly right. So what I'm showing here is as you increase these plots, as you increase the number of components, the amount of variance tails off. So one natural phenomenon that happens is you often only have a couple of components that really explain the entire data set if you're doing anything that's like sufficiently large and kind of coarse grained. And so you can manipulate only those 5 components and your conclusions, depend on those and maybe not the rest of the data set. So that data compression kind of teaches you something about the structure of the problem. These are awesome questions. So I'm going to skip to the last slide. We were only one slide away. We only skipped one beautiful picture of denoising. Look how beautiful it is. You got everything from it. So we saw the famous EM algorithm. This is something I wanted to show you because you decompose these things in latent variables. It's the workhorse that people use all the time. It's kind of the fallback that people are going to use there. We saw PCA, which is a workhorse of dimensionality reduction. The substructure for PCA was subspaces. The substructure for EM were these latent probabilistic model that we were able to solve. With that, I just want to say you folks have been phenomenal. This was a great quarter for me. I'm gone. This is my last class. And I thank you so much for, oh, that's sweet of you to say, but thank you so much for making this job so much fun. So please take some extra candy and have a great rest of your day. Thanks, guys.